Hello, this is
Joanna Piwko
and Sylwana Kaźmierska from Digica. And today we would like to talk about radar data and what tricks and tips we would like to share with you in case of classification of radar data. So what's the agenda for today? First of all, Joanna will talk about the basics of radars in terms of physics of them, what the parameters and data hidden in the radar signals, what's the background, what are they for, what are they used for, and then we will switch to the part in which I will talk about training models on radar data. How do we treat the Doppler frequency signals in practice in our commercial projects? I will also talk a bit about latent spaces and how do we use them in case of the radar data. The floor is yours.
Let's start from something you may know. Echolocation is one of the methods which animals like bats or dolphins use to navigate. So the animals is sending a signal, and if signal hits an object, then the signal reflects from it and back to the sender. And this is the method which animals use to detect how fast objects near them are moving. Okay, and now we have Doppler effect, which is connected with echolocation. And this is, you may also know from your experience. So when the ambulance is moving and it's approaching to you, the voice of the alarm is higher, and the frequency is also higher. And when the ambulance is passing you away, the voice has lower frequency. And this effect is used in radars. So what are the radars? The word radar is the acronym of radio detecting and ranging. It was used first time in 1940 by US Navy commander. And the radar is the whole set of equipment which send directed electromagnetic impulse, and when the impulse hits the target and back with reflected energy, and radar gets the signal, which is analyzed, and it is possible to say what is the target, how fast is it moving. And based on the echo of the reflected energy, we can determine distance and the direction of moving object. And one of the interesting story is that all data scientists know receiver operation curve was actually designed for measuring accuracy of radar, how accurate they are detecting enemy and the noise signal. Okay, so you may wonder where the radars are using. So the first applicants is Army. In Army, radars can be used for detecting targets in air, ground, or sea. Another usage is in aviation. So firstly, for aircraft, it is used to warn about all obstacles nearby the plane and display weather information or give accurate altitude readings. Another usage is in marine. So radars can help to prevent collision with other ships on the sea, or monitor and regulate ship movements. Moving on, we have meteorology. So radars in meteorology are used for short-time weather forecast. So, for example, radars sends signal, and if the signal hits the cloud, so meteorologists can say that maybe it will be cloudy, or based on the signal also can say if the rain will be or will be a tornado. Moving on, also in geology, radars are used for investigate what is underground, what materials are in underground, or if there are some cables or pipes. And another important usage of radars is in medicine. So in this field, radars are used for measuring vital sign or human activity monitoring, like sleeping monitoring or measuring heartbeat and respiration rate. Okay, so now let's focus on some essential parameters for the radars. First one is distance. So to measure distance, we need time when we send the signal and the time when we receive the impulse. And when we have a difference between the times, so we need to know the propagation of a radio wave, and it is constant. And if we know the propagation and the time difference, so it's easy to calculate the distance from radar to the object. Then we have the azimuth. So the azimuth is the angle between the north direction and the reference direction in the clockwise direction. This parameter depends also on the size of antenna of the radar. So in some cases, it can be not very accurate. So it's based on the beam size of the antenna. Then we have another type of angle. It's the elevation. So it is the angle between the horizontal plane and the line of sight measured in the vertical plane. And the reference direction is a horizontal line in the direction to the horizon. So if the object is above horizontal plane, the value of elevation is positive, and it is under horizon, it's the negative. And when we measure this angle, we can also calculate the height of where the object appears. And another parameter is radial velocity. So we can measure how fast is moving the object. And the last one is the radar cross-section. This parameter has unit square meters, and it says about the refractive of the object. So it is area of the object which reflects the signal. And for simple objects like cubic or sphere, it is easy to calculate, but on more detailed objects, it is not easy to calculate. And we have on this slide the table with some examples of values range for target types. And as you can see, some of the range of the values are very close. And this value, based on this value, we cannot say for 100% sure what is the type of the target. The interesting thing is that you may heard about the stealth technology, which makes plane invisible for radars. So the plane can be covered by special material, uh, which has very low RCS, and this makes plane invisible. Or the other thing is that the plane can send some radio impulse, and when the signal from the radar hits the plane sends the radio impulse and makes that sended from radar signal invisible due to diffraction or the interference of wave. Okay. Moving on, FMCW radar is the most common nowadays type of radar used. It is frequency modulated continuous wave radar. So this type of radar sends the continuous wave, not the impulse signal, and also its frequency is modulated, so it's changing in the time. It's not the same. And this type of radars has not one but two antennas, and one is dedicated for sending, and another one is dedicated for receiving signal. And this type of signal has one very major advantage, because it is useful for detecting non-stationary objects. So we can detect objects which are moving, like planes, ships, drones, or birds, or vehicles. And due to that, we can also measure how they are moving and their representation of velocity.
How do we then treat the Doppler frequency signals in terms of training our models? First of all, as Joanna said already, the radar data is time-oriented. So this fact makes it simple to divide those samples of micro-Doppler signals into smaller subsamples. And this actually has a twofold effect, because you can either use this one bigger block of data, which means we have a bigger image that might convey more information to the network, or we can divide them into smaller chunks, and this way enlarge the data set, which can be very fruitful in the long run. So it's kind of a trade-off, and we just have to decide whether we have a big enough data set for the training, and if not, maybe we should just have smaller chunks of data. In our case, the second approach proved us right, but of course it can vary depending on the case. As you can expect by now, even if you never worked with the radar data so far, those data can be treated exactly the same as typical visual data from the RGB domain, at least in some aspects, because there is this exception that, for example, we have to remember that it's just one layer of data. So in fact, it resembles more of a grayscale image, but it doesn't matter so much in the long run. For example, you can see over here, this is part of our neural network that we use in one of our projects. And as you can see over here, we treat radar data exactly as typical image input. Thus, the convolutions can be easily applied over here, just like in this layer. What's interesting is that we also can treat radar data as image data in terms of using latent spaces. So what are latent spaces then? Probably some of you already know and use them, but if not, just a small recap. Because neural networks usually consist of multiple layers, and they're like an input layer, output layer, and multiple hidden layers. Thank you, Captain Obvious. However, in fact, those latent spaces translate roughly to hidden layers, because latent means hidden here. But actually, why do we say latent if we can just call it hidden spaces or hidden layers? Let's start from the beginning. Please take a look at this image below. You're probably familiar with such network architecture as autoencoders, but if not, just a small recap that their purpose, their main purpose, is to simplify images by finding their core features. So basically, we are forcing this model to compress the data as much as possible, as over here in this bottleneck part. And this way to reduce its dimensionality, but this way only keeping the information that is very, very important for the reproduction of this image, just as we see in this bottleneck part. So on the right side of the image, we can see the piece of code that we use. That shows us the exact place where such a bottleneck can be found. It has two units over here, and as we will see later on, it will be very helpful for us for the visualization. And as you can see in this case, the image, the input image and the output image are exactly the same size. So in case of this autoencoder, we expect the model to output exactly the same object to the one that was inputted. As a side effect, of course, we will probably get images that are denoised, and it's a great feature. So to sum up, we want the latent space to store all of the data that's relevant, that has like relevant features in such a way that the model can, as accurately as possible, reconstruct it. However, the latent space is a completely abstract space containing feature values that we cannot interpret directly, which actually makes us ask, what do we use latent spaces for, especially in case of radars? We have to bear in mind that latent spaces are useful not only for what I just said. So why are they so important for us? So here are the two tips on how we use those latent spaces in real life projects, like commercial ones, and especially the ones like the radar data. So first of all, we use them, for example, when we want to generate important features, and we use for that unlabeled data. Let me explain. In case of radar data, there is such a problem that when we get images from the client, the radar signals, they usually can be counted in hundreds of elements. So as every data scientist knows, it's usually not enough for a neural net. So, but unlike RGB domain, there are usually not that many open source datasets to use them for the training. However, what is sometimes easier to get is some bigger dataset of unlabeled data. So what can we do with that? Well, that's when latent spaces actually show up. Let's suppose we have the exact neural network architecture as the one in the previous example, with such an exception that now we want to reproduce the radar data, not the MNIST images. So the point is that the features that will created in this latent space are something that we can actually use when we want to pre-process the labeled data later on. This labeled piece of data set that is not that large. And we hope that this intelligence that comes from this pre-trained latent space will positively impact our future supervised learning this time. To me, personally, using this knowledge on how to extract important features bears some resemblance to actually transfer learning, because we can share the learned representations for the classification that we do not that we do on our client's data later on. That's one purpose of latent spaces, and one place when we can use it, and we actually do so very often. And the second one is when we want to check what type of information is missing when we train our model. So that's an example of the plot that we sometimes do to visualize what the bottleneck part actually consists of, and what features does it, what weights does it have inside. So once we output those feature values for each image from the bottleneck, we can easily visualize the position of each image on this 2D plot. In our case, we outputted actually two values so that we don't even have to reduce this dimensionality of those features to show them on this plot. So this is the moment when we actually can assess which images look familiar to the network and which do not. Because knowing that, for example, this particular image belongs to different class that's all around it, we have a hint that we should somehow boost this signal on this image. So in other words, we would like the model to see exactly what we see. And this is actually the moment when filters come up, which can be applied to radar data exactly as the image data. So as we can see on the left side, we have this sample of the radar data. And actually the topmost part is the original signal that we got from our data set. And we know that we would like to boost up the signal that we see on the left side, this vertical one. So first of all, we just load it, for example, from NumPy. So this is the point when we would like to show you what filters were most useful for us in terms of preprocessing the radar data. And so let's take a look. First of all, what was extremely helpful was this very easy Sobel filter that probably all of you know. It's the filter that enhances the vertical signal. So we use this vertical Sobel filter from Sky Image Library. The second filter that was really helpful for us was this denoise TV Chambol filter. Please bear in mind that we have to scale the samples to have values between 0 and 1 before we do the filtering, because in the previous filter it was not that important. The third one is actually the same as the previous one, the device TV Chambol. However, we just play around with the weights of this filter. So of course we can play with the parameters to make them as suitable for our case as possible, because you can probably use completely different type of radar data, so feel free to play with the parameters. And the fourth one, or actually the third one, is the noise wavelet filter that's also denoising the image, and it's also very helpful in our typical projects with the radars. So thank you very much for your attention.
Thank you.
And feel free to ask any questions.